We now have come up with a biasing scheme that promises to reduce the sensitivity of transistor small signal parameters, the transistor's transconductance, with respect to the parameters of the transistor, such as the threshold voltage and current factor. Okay. So what we did was the following. Instead of saying that the transistor should be provided with a VGS of 3 volts, okay. So we know that if it's in saturation, it would draw a current of 200 microamperes. Okay. So instead of this, what we do is we have a 200 microampere current source, and we compare that to the actual drain current of the transistor, whatever that is. Okay. So now this drain voltage here, VD, will increase or decrease depending on the difference between this 200 microamperes and ID. So if ID is too small, it increases. What we realize is if ID is too small, we had to increase the gate voltage. So if we simply connect the drain to the gate voltage will be adjusted in the correct direction. So if ID is too small, this voltage will rise because 200 microamperes is more than ID, and the difference will flow into the parasitic capacitance at this node, raising its voltage, which raises the gate voltage. So ID increases and so on. So finally, the circuit settles down when this 200 microamperes and ID are exactly equal to each other, so that no current flows into the parasitic capacitor. Okay. So the circuit settles down to ID being 200 microamperes. Okay. Now why does this help? We've already worked out the expressions for Gm, Kn, the current factor, times VGS minus VT, or square root of 2 times Kn times the drain current. The first expression is useful when VGS is constant. Okay. So then you can see that VT will directly influence Gm and also Kn will directly influence Gm. Whereas here in the second case, which is useful when ID is kept constant, you see that Gm is dependent on the square root of the current factor. Okay, so if current factor changes by 10%, Gm changes only by 5%. We can also understand that by examining this voltage. What should this voltage be? I suggest that you calculate it by yourself and then compare it to what I have. The way you calculate it is by recognizing that in steady state, ID has to be equal to 200 microamperes or I0 in general. Okay. So we also know that if it is in saturation, ID will be Kn by 2. Kn, by the way, is mu Cox W by L, VGS minus VT squared. Okay. Now ID has to be equal to I0. So we can solve for VGS here, and we will find that it is VT plus square root of 2 times ID by Kn. Okay. So this is just some algebraic manipulation, but what does it tell us? It says that if the transistor had larger VT than you expected, what would happen in this case? If the threshold voltage is larger than you expected, the current would be smaller. But in this case, you can see from this expression, if VT is larger than you expected, VGS also would increase correspondingly. Okay. So a transistor with a larger VT will automatically get biased with a larger VGS. Similarly, if the current factor is smaller than you expected, so in this case you will get a smaller current. On the other hand, here what happens, you can see that Kn is in the denominator here. If the current factor is smaller than expected, VGS increases. Okay. So a transistor with a smaller current factor automatically gets biased with a higher gate to source voltage. Okay. This is exactly the kind of feedback that you want. It's basically saying that given this current, the gate source voltage will get set automatically, and that VGS value will be larger if the threshold voltage is larger. It will also be larger if current factor is smaller. That gives you an understanding of why the variation of Gm will be smaller. For instance, in this case, if the threshold voltage is larger, VGS would be correspondingly larger. So this difference remains constant. Similarly, if Kn is smaller, VGS will be larger, so that compensates this to some extent. Okay, so that also comes out here, because in this particular circuit, in the second circuit, VGS is not fixed. Okay, this expression is always correct. You just have to apply the correct value of VGS. Is this okay? So essentially, this negative feedback is a way of adjusting the VGS in response to changes in transistor's parameters. Okay, a transistor with a higher threshold voltage or a smaller current factor will automatically get biased with a higher VGS, compensating for the effect of the higher threshold or lower current factor. Okay.